Hello and welcome. Today we're going to discuss the binomial theorem and we're going to prove the binomial theorem. So the binomial theorem is basically this formula here. A plus b to the n equals the sum from k equals 0 to n of n choose k, a to the k times b to the n minus k. It's a very famous formula. It's used a lot in mathematics. It's used in different branches of mathematics. It's very important. It's very useful in proving other results. And the n choose k on the right hand side basically is equivalent to the number of ways that you can select k objects from a total set of n objects. For example, if I have 10 apples and I asked you to choose 5, how many ways can you do that? It's 10 choose 5. So n is 10, k is 5. So we show it's true for the simplest case, n equals 0. That's the most basic elementary case. Pretty standard, straightforward. And then what we'll do from there is we'll show that it's true for n plus 1, which means that it's true for 1. But then that causes a domino effect. That's proof by induction. So that means it's also true for n equals 2, which means it's true for n equals 3, and so on. So for n equals 0, the binomial theorem says that a plus b to the 0 equals the sum from k equals 0 to 0 of 0 choose k, a to the k, b to the 0 minus k. Simply plug in n equals 0 into the original formula. So the left hand side is clearly 1. You know that anything raised to the 0 is 1. And the right hand side is 0 choose 0, a to the 0, b to the 0 minus 0. Well, 0 choose 0 is 1. We proved that in another video. We proved that anything choose 0 is 1. A to the 0 is 1. We know that anything to the power of 0 is 1. And b to the 0 minus 0 is b to the 0, because 0 minus 0 is 0. So b to the 0 minus 0 is also 1. So 1 equals 1 times 1 times 1. And the bit in the brackets is 0 choose 0, but I've just done it out in factorial form, and that's what it equals. 0 factorial over 0 minus 0 factorial, 0 factorial. So they're all just 0 factorial. They're all just 1. 1 over 1 times 1. So everything there is just 1. So we're saying that 1 equals 1. So we've proved the binomial theorem for the case n equals 0. So now we're going to start the inductive process. So to prove by induction, we prove that a plus b to the n plus 1 equals the sum from k equals 0 to n plus 1 of n plus 1 choose k times a to the k times b to the n plus 1 minus k. So all we've done is we've replaced n by n plus 1 in the original formula. So a plus b to the power of n plus 1 is equal to a plus b times a plus b to the n. Because a plus b is just a plus b to the 1, so the bases are the same, multiplying, so we add the powers. So a plus b to the 1 times a plus b to the n is a plus b to the n plus 1. So we've just split it up into two numbers, and then we can split that again. These are just algebraic tricks. So we can say that's equal to a times a plus b to the n plus b times a plus b to the n. We've basically expanded the second line. So now we need to work out what are these things. What is a times a plus b to the n, and what is b times a plus b to the n? We need to find out what they are in factorial form. So the original binomial theorem states that a plus b to the n equals sum k equals 0 to n choose k, a to the k, b to the n minus k. That's in yellow. That's the original binomial theorem, or binomial formula. And that's equal to n choose 0, a to the 0, b to the n, plus n choose 1, a to the 1, b to the n minus 1, plus dot dot dot, plus n choose n minus 1, a to the n minus 1, b to the 1, plus the final term is n choose n, a to the n, b to the 0. And before I proceed further, just a couple of little things to note here. N choose 0, we discovered that earlier, is 1, and n choose n is 1. With the first term and the last term there. So now we're going to work out a times a plus b to the n. So all we really have to do is multiply every term by a. So that first term, you'll notice we have an a to the 0 times a b to the n. So that's going to become a to the 1 times b to the n. The second term has an a to the 1 b to the n minus 1. That's going to become a to the 2 b to the n minus 1, and so on. The final term will have an a to the n plus 1, because we multiply them all by a. So that's exactly what we get. We get that. I'm not going to go through it all again. Just multiply everything by a, and you get that. And then we do the same for b times a plus b to the n. You multiply everything in the original formula by b. So if you go back up here, multiply all these by b. So the first one will be a to the 0, b to the n plus 1. The second one will be a to the 1, b to the n. We're just adding 1 to each of the powers of b. And we end up with that. So have a look over that for a second. So there's our a times a plus b to the n. And there's our b times a plus b to the n. And you'll notice that all the a's have a power, all the b's have a power. So now what we're going to do is gather them together, gather the common ones together. So we only have one a to the 1 b to the n. Sorry, we have two of those. We have two a to the 1 b to the n's. We have an n choose 0, a1 b to the n. And here we have an n choose 1, a1 b to the n. But the first term in this one is a to the 0, b to the n plus 1. But we don't have that in the a1. So that'll sit on its own. But in the a1 we have the final term with a and b power of a to the n plus 1, b to the 0. We don't have that in the b terms. So that will sit on its own as well. So all the ones in the middle, they are coming twice. So we've got a1 bn, a to the 1 b to the n, and we've got that there as well. And then we're going to have a to the 2 b to the n minus 1, and so on and so on. They'll all come twice. So now we're going to gather them all together. So you add the two things together basically. So that's the first one that sits on its own, n choose 0, a to the 0, b to the n plus 1. That comes from the b times a plus b to the n expansion. And then we have an a to the 1 b to the n appearing in both expansions. One has an n choose 0 coefficient and the other has an n choose 1 coefficient. Add them together and we get all of that. And we do the same for all the other terms. And it's got a nice pattern, a nice flow to it. So the power of a and the power of b always add up to n plus 1. That's no accident. The power of a is the number which is the k value for the second component on the left hand side. So n choose 1, so 1 will be the power of a on the a to the 1 b to the n term. And then for the next one down, you've got n choose 2 as the highest number in the component on the left hand side. So the 2 there will be the power of a, and 3, etc. And keep going like that. And for the b power, you've got b to the n minus the number, the k number on the left hand side. So the k number on the left hand side for the first one is 0, so it's b to the n minus 0 with the power on the right hand side. And then the next one down is 1, so you've got b to the n minus 1. So there is a pattern and a flow to it. I hope you can understand and follow that. And then the final term is on its own, is n choose n, a to the n plus 1, b to the 0. We met that earlier in the a times a plus b to the n expansion. That's it there, it's the last term. So that sits on its own when you add the two together. And now, using three results from my other video, namely n choose 0 equals n plus 1 choose 0 equals 1, n choose n equals n plus 1 choose n plus 1 equals 1, n choose k plus n choose k plus 1 equals n plus 1 choose k plus 1. So we're now going to use those three powerful results to finish the proof. So the equation can be written as a plus b to the n plus 1 is equal to n plus 1 choose 0 times a to the 0 b to the n plus 1 plus n plus 1 choose 1 times a to the 1 b to the n plus n plus 1 choose 2 times a squared b to the n minus 1, and so on, all the way down to n plus 1 choose n plus 1 a to the n plus 1 b to the 0. So I hope you can follow all of that. So for that first one, n choose 0, a to the 0, b to the n plus 1, what we've done is we've replaced the n by n plus 1. We're allowed to do that because they equal the same thing. They equal 1. With the second one, n choose 0 plus n choose 1 times a to the 1, b to the n, we have replaced that with n plus 1 choose 1. And that comes from that third result. And all the rest follow like that. And then the last one, n plus 1 choose n plus 1 times an plus 1 b0, that comes from that last term there where we've replaced n with n plus 1. We're allowed to do that because n choose n is 1, n plus 1 choose n plus 1 is 1. So if the n and k are equal, the answer will be 1. So you can replace it with whatever you like as long as the two stay the same. So that is an equivalent statement. So when you put all that together, and then we want to rewrite it back in the form of the binomial formula, that equals the sum from k equals 0 to n plus 1 of n plus 1 choose k, a to the k, b to the n plus 1 minus k. And if you just quickly check all of those, you'll see that that checks out. And that's the binomial theorem with n replaced by n plus 1. And there you have it. We have proved the binomial theorem by induction. So that concludes the video. Have fun with the binomial theorem. Thanks for watching. Please subscribe, and I'll see you on the next video.